And so now let's calculate and find the mass flow rate of the air. So we have that this is m dot A times 1 plus RFA times C sub P times T 4 prime minus T 5 prime. And that's going to be equal to 20,000. So if I substitute in here m dot A times 1.0149 times 1.0047 times 984 minus 743 is equal to 20,000. We get that m dot A is equal to 78.3 kilograms per second. And I can find the volume flow rate. V dot 1 is equal to m dot R T1 over P1 is equal to 78.3 times 0.287 times 300 divided by 100. And we'll see that the volume flow rate is significant. It's 67.4 cubic meters per second. That's a lot of flow rate. So, I mean, this is a big engine, but you're looking at jets, so jet engines would be having volume flow rates like this or greater. And that's why they're huge. And so you can look on YouTube and you can look up actual jet engines from GE that go on the Boeing planes, and you'll see that you see the size of people and the size of the engine. And so we can find the mass flow rate of the fuel is m dot A RFA .3 times 0.0149 times 60 seconds per minute. And so we have m dot F is 70 kilograms per minute. So that's the fuel flow rate. The thermal efficiency is WT2 over m dot F or RFA H sub RP. So this is 1.0047 times R sub F A 0.0149 times 984 minus 743 divided by 0.0149 times 44,102. And so we get that the thermal efficiency is about 37%. And we were asked to find the temperature leaving, so I wanted to find this temperature. And so Hx, so first law on the regenerator, Hx minus H2 prime is equal to 1 plus RFA times H5 prime minus H6. And so I have 1.0047 times Tx 725 minus T6 T2 prime 6 28.5 is equal to 1.0149 times 1.0047 times T5 prime 743 minus T6. I solve for T6 at last. T6 is equal to 651.5 degrees Kelvin. So we're able to find the actual exit temperature leaving, and we've extracted some of the energy that would have been at T5 prime has now gone into the air. So we've used that effectively for regeneration. Now, in the text, examples 14.5 and 14.6 and so what they look at is the benefits of adding a regenerator to an actual system. And it uses compressor efficiencies, turbine efficiencies, but the analysis is done with these PR relationships, which I don't want to do. And the problem we just did had all the complexity of what we did of these problems. It's just that I didn't do the simple system beforehand. But the results indicate, so the results are interesting from this, and that's what I want to get. So the results indicate that the thermal efficiency increased from 28.8% to 35.5%. So that's a big deal. And the fuel-air ratio, went from 0.017 to 0.0129. And so when I look at that, again, it's a significant decrease. So adding the regenerator is very much worthwhile in terms of your fuel consumption, your thermal efficiency. Obviously, the two are related. So it's a good investment if it's a stationary plant running at stable conditions. Obviously, if you had a variable plant, it may or may not be worthwhile in terms of the capital costs. And so one of the things that we could do as well is we could have this regenerative cycle for a closed Brayton cycle. You're going to say, oh, hey, I have to have this for a closed Brayton cycle. Why? And what we're going to do is it gives us an idea as to when we would want to use a regenerator in terms of basically T3. So what I want to do is draw this closed regenerative cycle and look at what this is going to tell us. Just like the Otto cycle could give us indications of improvements with compression ratio, etc., we can have the same thing here. And so this is going to be a closed regenerative cycle. Regen Brayton. And it's figure 1416. So if I do this, I have a compressor. It's going to go through a regenerator. Here's a regenerator. Okay, so I have the compressor. It's going to come out here at X. Goes into a heat exchanger. Heat in. Heat in. Going to go into a turbine. Out of the turbine into there, and here we're going to have turbine work. And oh, that isn't true. And then I have to go into a heat exchanger, heat out. It just shows I should look at my own drawing beforehand. So I'm replacing the exhaust with a heat exchanger. I'm replacing the fuel going in with the heat exchanger. And now this comes out. So basically it goes out, then I have heat out, and this is the exhaust part. So now I can do 1, 2, X, 3, 4, 5. So I have this. And so and here's the regenerator that we had before, and on the TS diagram, I go 1 to 2. One to 2, 2 to X, X to 3, 3 to 4, 4 to 5, and then 5 to 1. And again, what this is showing us that this area and this area, the areas are the same. So this is the energy given up, and this is the energy gained. And now what happens, because this is a Brayton cycle, we can make some assumptions and get in a closed form efficiency for the regenerative Brayton cycle. So the thermal efficiency is equal to W net over Qin. It's 1 minus Q out over Qin. It's equal to 1 minus T5 minus T1 over T3 minus Tx. And so we have that information for an ideal counterflow heat exchanger. We're going to have that Tx is equal to T4 and T5 is equal to T2. And if I, from PV to the K equals a constant, we have that T2 over T1 is equal to P2 over P1 to the K minus 1 over K. So this is equal to T3 over T4 as well. And so the thermal efficiency reduces to this form. 1 minus T1 over T3 to R sub P to the K minus 1.